Okay, now we'll actually
the
get
first
started.
thing that pulls up is Escapology Orlando.
So how you guys doing? You guys feel okay about the homework? No?
Yeah.
Oh.
It wasn't that bad. I just don't know where some of the equations cannot be used.
It's hard to find them.
What do you mean?
Like if, for example, the distance modulus equation, if that can only be used for distance of galaxies or stars, or I know that one there's just distance, so it doesn't matter. But some things like that.
Okay.
Well,
We'll go through it. Any place where you're like, I don't know about that one, holler and I'll try to flesh it out. So, distance modulus for itself is just that thing, and you can plug whatever you want to into it as long as they're magnitudes. But I guess there are a whole buttload of equations that you need to use, and knowing when to use which one is important. And knowing when not to, and actually let me, here's the thing that I really need to learn, that I need to put it in the first lecture, because but maybe it's better if everybody just stubs their toe on it and then I tell you. I'm not sure. So when I give you a proportionality, you can't plug that in. If I give you a proportionality between two things, you can't get numbers out of that. So I give you something like period to the some power is proportional to the luminosity. You can't get numbers out of this, because this proportionality means I'm skipping some large piece of information. This is the behavior, but what this actually says is that the period to some number is equal to some other number that I haven't given you, that you have to find somewhere, times the luminosity, for instance. This is one that a bunch of people did. And that's all right, because a bunch of people do this all the time. I just forget to say it out loud. So if there's a proportionality, you can't get numbers out of it. You have to find a different equation. Or if I'm asking for a fraction and the actual proportionality drops off, if that can disappear because you're looking at a ratio of things, then you can use a proportionality. But only if you're looking at a ratio of things. If you're looking for the absolute luminosity of something, for instance, then you need to go find a different equation. And I'll show you where that other equation is. If you happen to pick up the right one from the notes, then you were good. And if you grabbed the wrong one, then you weren't. So I'll go through that too. Oh, let's see. I got to pull up the homework. Let's go through the homework. No. Ding. Okie doke. So, Barnard star is one of the closest stars in the sky to us. And so you measure it in January and then again in June, and you find that after 6 months, the star had shifted 1,000 milliarc seconds on the sky. Now, I could have said arc seconds, but 1,000 milliarc seconds is, usually these things are measured in milliarc seconds. How far away is it? So all you do is measure that it goes from here to here, from from January to August, or January to June. How does it move? So most people got this one just fine. A couple of you had a 2 in the wrong spot. Let me show you where that 2 is supposed to be. So here's the sun. Let's make the sun yellow, because I can. Here's the sun. Here's the Earth. Here's the Earth in January. Here's the Earth in June. What is the distance from here to here? 2 AU. Very important. Now, the star that I see moves from here to here. Let me see. Here's the star. Here's the foreground stars that they move relative to. So I'm just going to draw it this way. Here's the angle that I measure, P. The distance, this is actually 2P, because the parallax distance is at 1 AU. So you want to divide it by half. We do it to get a longer baseline so that it's a little bit more accurate, but then you got to divide by 2. So the distance is P over, sorry, just 1 over theta in arc seconds. So, but since this is 2 theta, you need 2 over theta. So it's, sorry. I didn't plan this one ahead well enough. You need just P, so you need a 2 up top to get rid of that 2. Does that make sense? So I gave you this whole angle. I said how far it moved by, which is twice the parallax shift, because the parallax shift is only at 1 angle. So some of you had a 2 in the wrong spot and were off by either 2 or 4. Yeah, let me know. So it should look like this. So it should be the distance is twice over the angle that you get from over 6 months. Times 10 to the minus 3, and that's just typeset wrong. So you should have gotten 1.8 parsecs. So you'll notice that the geometry ones give us answers that are like 10 parsecs, small numbers of parsecs. And then the other ones give us things that are like 1 million parsecs, because that's the difference between what the 2 tools are used for. That some of the tools are for close things and some of the tools are for far things. This one is for close things. Andromeda has an apparent magnitude of 3.58 and an absolute magnitude of minus 20. How far away is it ignoring galactic extinction? So if you ignore galactic extinction, then it's just little m minus big M divided by 5. Add 1, raise all that to the 10. Very important that you use 10 and not E. All of the logs in all of this, all of the logs are base 10. So a couple of you used natural log and were off by a factor of 10 in a couple of places. But it's okay. I don't think anyway, 10 versus E makes a big difference in this. So without extinction, you get a distance of 600,000 parsecs. And with extinction, we just add in the extinction here to the distance modulus. And I told you it had an extinction of 0.48. That's the total extinction. So you just drop that in and you get a slightly smaller distance of 5.5 instead of the 5 parsecs. Has anybody got any questions about that? Pretty good. Okay, the star V1 has an apparent brightness of 18.2 and a period of 31.4 days. V1, this star is the star that Hubble first used to determine the distance to Andromeda. So this is an important star. So using the period luminosity relationship in the visual band, compute the distance to V1. And so here, the period luminosity relation is on one of the slides, and looks like this. And there were several, on one of the slides, there were several different relationships in several different bands that I put up. So that's the right one to use. The ones where there's proportionalities don't get you actual numbers, so you can't use those. They get you something that's kind of close, but it isn't correct. Okay, so from this formula, we find that the absolute brightness is minus 5, and then from the distance modulus, we get a distance of 500,000 again. You ought to get a number that's basically exactly this one, because this star is in this galaxy, so you should get the same distance. Okay, a binary system with masses 1.2 and 0.9 has a period of 3 years and an angular separation of 235 milliarc seconds. What's its distance? So you watch your units better. So a lot of you had trouble with units, or some of you had trouble with units. The basic idea is we need to find out how far away they are apart using the period, using Kepler's law. And then we use geometry, which is just, again, the distance over the parallax to find the distance. So Kepler's law says a cubed equals 4 pi, a cubed equals period squared, let's call it t, I call it t there, period squared times G times M1 plus M2 over 4 pi squared, all of this to the third power. Oh, the third's over there. So the easiest way to do this is to do everything in CGS and go from there. So G in CGS is 6 times 10 to the minus 8 centimeters cubed per gram second squared. And a solar mass is 2 times 10 to the 33 grams. You can look those up. This is the easiest way to do this kind of problem, is put everything into CGS and then get it back. But you got to be careful when you're doing that. So you should have gotten a distance of 2.6 AU. I don't know what that is in centimeters because I didn't write it down. So that's the semi-major axis is 2.6 AU. And then I told you what the parallax is, and then it's just that distance divided by the parallax gives you a total distance of 11.3 parsecs. Yeah.
Why do you not divide parallax by 2?
Because I know what the baseline is, because I know what the distance is. So the way the math works is let's see, distance in parsecs is 1 over d equals r over p. This is in parsecs, this is in AU, and this is in arc seconds. So you just need 1 AU. So when I did this for Barnard's star, I had 2 AU on the baseline, so I need to have 2 here. Whereas when I'm doing this here, I've got 2.6, so I need 2.6. Makes sense? So it's just how long is the baseline, how long is the angle versus the angle. Yeah. So a parsec is an AU divided by divided by an arc second. And that's all there is. So you need to know the distance in AU gives you the distance in parsecs, but you got to use the right distance. So we have to use 2 in the first one. That's the answer that I like. Sorry, that might have been a little confusing. Okay, any other questions about this one? So when you're doing these problems, don't try to remember, oh, is there a 2 or not? Just draw a triangle. Look at the triangle. Look at the baseline. And you can't just say 1 over theta, because it's usually not 1. It's the distance, it's the baseline over theta. Okay. A galaxy observed carbon monoxide emission peaks at 110 gigahertz. That's how I see it. That line's rest frequency is 115 gigahertz. So how fast is it moving? And what's its redshift? And what's its distance? So the redshift is easy. It's just, actually, this is incorrect, but you get about the same answer. This should be lambda minus lambda naught over lambda. But you get a similar answer. You get about a little less than 1. The velocity, you should get about 13,000 kilometers a second, or 13 million meters per second. That's a very large distance. It's a very large velocity, but we're talking about the expansion of the universe. The distance is just v over h naught. Is just 1.3 times 10 to the 4 divided by 70 should give you a distance of 186 million light years, which is substantial. Any questions on that one? I think everybody got that one. Okay. Supernova has a peak brightness of 11.7. That's what I measure it at. Then 15 days later, it's 12.6. That number goes up because the brightness goes down. So what is its distance? So you first find the absolute brightness from delta M15. And so, okay, delta M15, what does this look like? use the positive one. That's the short answer. So my supernova light curve, here's time, here's brightness. Let's call it MV. This is the peak, and I'm going to call this little MV because this is what I observed. This is the peak, and here's 15 days later, and here's delta M 15. Always bigger than 0 because supernova always get dimmer. A couple of you used the wrong sign on this and got different answers. I don't think I took points off for that, but I tried to notate it when I did. So you should get an absolute brightness of minus 19. Sorry, I thought I had something interesting to say about that, but I don't. And the distance modulus of that difference, and then you just plug it into, you just exponentiate, and you get 16 million years. Number 7, everybody did. Okay, any other questions about anything on the homework? Everything make sense? Let's see, what else am I doing today? Yeah. We'll do motion in a second. I'm going to finish up on measuring magnetic fields and summarize, because if I spend a second summarizing, then I can ask you questions about it. So new stuff. Okay, so I went over 4 ways to measure magnetic fields in the interstellar medium, and really in all of astrophysics. These work for extragalactic sources as well. Some of them work for extragalactic sources better than others. So we talked about polarization. And here we see this mostly in the infrared and in the millimeter and a little in the radio. It's good for the plane of sky. So each one of these methods is only sensitive to one of the 2 components of the magnetic field. Either it's the component along the line of sight, or it's the component in the plane of the sky. So I'm going to separate those 2. So I'm just going to make a list of these techniques and notate that. So I'm going to write down where they're all used and what components they're good for. And the basic physics is dust is tied to the magnetic field and spins around, and that the dust gives you a polarized signal because it's long and skinny. We talked about Zeeman splitting. This is mostly seen in the radio. I don't know if there's any Zeeman splitting lines in the infrared or optical. This is a shortcoming of mine. But actually I need to sort out in a hurry because a friend of mine wants to build a satellite, and I don't know how to do that, and I don't know if the thing that he wants to build is actually useful for me or not. So I gotta learn more about Zeeman splitting. Zeeman splitting is only good for the line of sight magnetic field. And this is magnetic field lifts of degeneracies in atomic levels. This one is really hard to do. It can get you the plane of sky as well if you have an incredibly good telescope, but I don't know of any measurements on any astrophysical body that have actually been successful at doing that. They try to do it on the sun a little bit, but it's really hard to do. So really it only gets you the line of sight. The next one is synchrotron. Synchrotron emission. This is mostly in the near infrared, and this is only good for the plane of the in the radio. I'm talking about huge amounts in the radio. This is good for the plane of sky because we've got these electrons that spin around the magnetic fields, and they're polarized in that direction. And that polarization is what lets us measure the synchrotron radiation and know that it's synchrotron radiation. You have electrons spiral around E. And then the last one that we talked about is Faraday rotation. And this is also in the radio, and it's good for the line of sight. And in this technique, polarized signals are rotated by the plasma. So these are the four methods that we've used to measure astrophysical magnetic fields, and all three of them have been used. Three of them have been used for astrophysical for extragalactic objects. I don't know of any Zeeman splitting measurements in extragalactic objects, but that might be my ignorance. So. All of these are used both for within our own galaxy and for external galaxies. So one of the weird things is one of the weird coincidences in the universe is that the kinetic energy in the galaxy. Yeah.
What is the form of
Dust tied to B.
Oh.
So the kinetic energy in the galaxy, and the energy in cosmic rays in the galaxy, and the energy in magnetic fields in the galaxy, the total energy, are all about the same. Why? Because they all feed each other and create each other. So the kinetic energy in the galaxy spins up the magnetic field like a taffy puller, like this guy here. So you get twisting and stretching motions in the galaxy, and they're actually more helical than this, but this gets you the idea. So what's happening here, so this is a taffy puller. You get this gooey stuff, and you stretch it out like crazy, and the more you stretch it, the longer the polymers get, and the longer the polymers get, the chewier the candy gets. So it starts off like a crumbly dust, and then you work it until it works into this chewy stuff, because these polymers all get really good and long. A magnetic field is the same way. You have motion. Here's a schematic of the sun. You have motion in the sun. You start off with a field like this, and it gets twisted up like crazy, and you get a field like this that's stronger. You don't need to follow that too much. Basically, the kinetic motion in the galaxy twists up the magnetic field, and it does that until it can't anymore. That's when the magnetic field is about as strong as the kinetic energy. So once the kinetic energy has amplified the magnetic field so that they're about the same energies, then it can't amplify it anymore. And the magnetic field amplifies all the cosmic rays, because the cosmic rays get amplified by all the magnetic fields, so and accelerated by the magnetic fields for reasons that I'll show you later. So we have these three things that are all related to each other, and this is true probably for most galaxies. Okay. That's all the rest I'm going to say about measuring magnetic fields. All of this will probably show up on homework, because I like this stuff. Let's see. Is there anything else about galactic structure that I want to talk about? Yeah.
How is the magnetic field related to cosmic rays?
Oh, the magnetic field accelerates the cosmic rays. So the cosmic rays get their energy from the magnetic field, and they just suck out as much as they can. So they have about the same energy as the magnetic fields, because that's who's making them have a high energy. So let me give you the utterly confusing. I'm going to give you a completely unsatisfactory description of the completely confusing topic of diffusive shock acceleration. So what happens when I have a star that then blows up in a magnetized uniform? So I have a star that explodes, and I have this magnetic field. This magnetic field gets stretched and compressed, and has the crap beaten out of it by the supernova, and we're left with this pancake of very dense magnetic field. And I've got these, so I'll have a shock front where the magnetic field is good and dense, and then the rest of the interstellar medium where the shock front isn't nearly as strong. So charged particles, like protons, are traveling through here. They see this very high magnetic field, and their gyro radius goes down very fast. So they're on some kind of arcing orbit that's kind of round, and then they get some really high, really tight curvature, and then they get accelerated like that. So they run into this wall of magnetic field, and they get bounced off because the gyro radius goes way, way down, and so they just get hooked around really fast. And this happens a whole bunch, and it's all kind of chaotic. It's not just like a smooth shock. There's chaos in the magnetic fields, and that chaos is necessary for amplifying the rest of the cosmic ray energy. Mathematically, that's kind of a nightmare, so we'll skip it. Okay, I think that's all I have to say. Any other questions about the structure of our galaxy? I'm going to hope to get through all of this in one day. What time is it? I got it now. Yeah, good. Okay. So I'm going to talk about how we measure our motion in the galaxy. Why do I care about that? Let's talk about that first. So I care about the motion in the galaxy because I need to know how big it is. I can't measure the mass, but I can measure the velocity and I can measure distances. I have absolutely no way of measuring masses, but I can measure velocities and distances. So I'm going to make a measurement of the galaxy and we're going to say that v squared at a particular point has got to be equal to g times the mass that's less than that point over that point. So the velocity is proportional to the mass. And this is what we call the dynamical mass rather than the luminous mass, because this is about the dynamics of the gas, not how much light I'm seeing from the gas. So now if dark matter isn't really a thing, then this is an approximation that works pretty well but isn't accurate. If dark matter is really a thing, then this is totally accurate. So we need to know how V behaves with mass and position. And what's found observationally is that this tends to fall off and do some weird things because the bulge has a lot of stuff going on. And then it gets flat. And this flatness is weird because the stuff tends to fall off. So the light stops around here, but I still have a crazy velocity out here. So we want to measure omega as a function of r, which is the rotational velocity, or the angular velocity. And we also want to measure d omega dr, which is the slope of the angular velocity. And this, we're going to see, is close to 0. Because at the solar circle, we're largely in solid body rotation. So that's the important thing, is that this curve has gotten flat by the time it's gotten out to us, which indicates that there's dark matter because the light's falling off. The velocity is not, which means there's something else that's keeping everything going really fast. So what we're after is omega and d omega dr. So let's get to that. So let's set everything up. So what does the galaxy weigh and what's its mass? I said all that. I said all that. So here's our coordinate system. So we have these three velocities, u, v, and w. So w is up and down, v is in and out. No, u is in and out, and v is round the disk. So v is the thing that I want to measure. V and r are related. Omega is v over r. But I can't measure that direction. What I can measure is a lot more complicated. So here's my schematic. The sun has some velocity here, which I can't ignore. This star, wherever it happens to be, has some velocities pointing in this direction. It's mostly tangential to the circle. But what I can measure is this component of velocity. And I can measure, if I'm careful, I can measure the tangential component of the velocity as well. Those are pretty tricky. Oh yeah, here we go. So this is the main velocity that I want to measure, but what I can measure is this from the proper motion, which is a difficult measurement to do, and this component, which is the radial motion, which is an easy measurement to do. So, but what I want is not this or this. What I want is this. So that's tricky. So we got to do some geometry and try to figure out where we are. But first, we got to figure out what the sun's velocity is. So this little red one, let's talk about that guy first. Pretty sure that's what we talk about. I spent all my time grading homeworks and none of my time flipping through my slides to remember what the hell is in the slides. Sorry about that. Give me like 4 seconds. Remember what I'm supposed to say here. Yeah, so we have all of this randomness, and that's part of the story that we've got to sort out. I think I went over this a little bit in class when I went over the readings, but I'm going to talk about it now. So let's talk about the distribution for all of these quantities. So if I look at, let's say this is going to be a velocity, and here's 0 velocity, and we're going to look at u, v, and w. So let's look at w first. So w is going to be shaped basically like a Gaussian, because everything that tends to is a Gaussian. Or if it's not, we're going to call it a Gaussian because it's an easy function to use. So anything that's peaked in the middle and falls off smoothly, we can approximate with a Gaussian. And as physicists, we do, because I like Gaussians. Is it specifically actually a Gaussian? Well, that doesn't matter for me right now. I've got some distribution. So there's some width because I've got some things that are moving with, let's call this W. Some things that are moving with, that are going up out of the plane. Some things that are going back down out of the plane. So I've got some things. So here's my galaxy. It's spinning like this. Some things are going up. Some things are going down. Some things are going up kind of fast, but really not very many things are going really fast. Some things are going down really fast, but really not very many. Most things are going kind of, mostly not moving up and down, but a little bit moving up and down. So we have a Gaussian in W that's centered at 0 and has some width. We'll call it sigma. Call it sigma W. Are we good with that? Now, U is the radial in and out motion. Well, statistically, I got to have as much going out as I have going in, otherwise the galaxy is exploding or contracting. So U is going to be a different Gaussian with a slightly different width. Those two widths will be related to each other, but I'm drawing it with a different width. And then W, and then V, which is the one I care about, V is the motion into the plane or out of the plane. And that all is distributed like this. It's not centered around 0, it's centered around 270 kilometers a second. Oh, I have the wrong camera on. Centered around 270 kilometers a second because everything in the galaxy is moving around at 270 kilometers a second. So this is what the random crap is doing. So I look up in the sky and I see all these stars. And I measure all their velocity. So I take each one of these stars and then I make a measurement of what the velocity is doing. So now the purple is my measurement. Now I gotta sort out radial this way versus radial in the plane of the galaxy, but that's okay. It's just a little bit of geometry, and I'm going to go through some of that geometry in an unsatisfying way in a minute. When I make this measurement, say I measure the W component, which is the up and down component, I'm going to get that. Here is 0, here's the velocity. This is W. And it's centered at some other number, W naught, that's not 0. This is what I measure. So why does the distribution of vertical velocities that I measure, why is that not centered at 0?
Is it because they're also moving?
Yeah, it's because I'm moving too. So if I have a whole bunch of things that aren't moving and I'm running through it, if I measure the velocity of all those things, I'm going to get my velocity as long as that's stationary. So I measure the velocity of a bunch of random things, and I get my velocity out of that, which is kind of awesome, because I know that this random population is centered at 0. So I can just shift it over. And the same with R. U. And the same with V. So, where am I? Where's my control? Okay, so this defines, when I go through this process, this defines a U, V, W, that is the velocity of the sun, relative to what? Relative to going around in a circle at 270 kilometers a second. On a circle. So, and that velocity, do I have it up there? I don't remember it off the top of my head. It's like 10. Where'd it go? It was right there. Huh. Oh, there it is. It's minus 10, 5, 7 kilometers per second. So that's the sun's velocity relative to what? And I just said it, but we call it something. This is a number. This velocity is relative to something. Nope. There you go. This is relative to the local standard of rest. Yeah, so this is relative to the local standard of rest. This is this circle that's moving. This local standard of rest is a velocity, not a position. It's the system rest. It's the velocity that things are at rest with. So we go through this stunt and we do a little bit of math that I'm not super worried about right now. Some things are related. We can get this number, and we can get the number for everything. Then we need to figure out how everything is moving in the galaxy. So then we got to figure out what's going on. So we have this whole page of math to sort out what our velocity is. That defines the local standard of rest. Then we have to go figure out, then we go measure again what everything is doing and say, okay, where are all these stars going? How fast are they going? How are they moving relative to the center of the galaxy? These distributions are relative to me. I want the distribution relative to the center of the galaxy now, so we've got to do a little bit of math for that. So we do this measurement with just the local stuff, the stars that are close to us that we can measure real easily. So that's an easy measurement to make, because we don't need the rest of them. So here's what I got. what do I talk about first? Or constants. Okay, so I'm going to talk about 3 different regions of the galaxy, just like the book did. I'm going to talk about near the sun. I'm going to talk about inside the sun, and then I'm going to talk about outside the sun. So near the sun, we can measure all 3 components of the velocity, because we can measure the proper motion of the stars. So for the stars where we can measure the proper motion, we can get the rotation curve. And remember, what we're looking for is omega, or d omega dr. So here's a page of geometry. I'm not going to go through it in a satisfying enough way because it's very weedsy and you'll get lost and it's not fun. It's fun to go through all the geometry by yourself. Watching me do algebra is not very useful, but I'll tell you what to do. So the radial velocity is what I care about, VR star. V star is what I want to measure. So actually, let me set this up. So here I have the galactic center. Here's us at a distance r0 from the galactic center. We've got to sort out r0 somehow differently, but I'll talk about that later. So you got to measure r0 somehow. This distance here, r, never going to measure this distance. The distance from that point to that point where I have, like, that's a real hard thing to do because I got to know exactly where both of those things are along their lines of sight. So that's difficult to measure. So we want to try to avoid having to measure big R because that's really hard to measure. What we want is V star, but what we can measure is VR star and VT, which is not drawn on this tangential. So just do a little bit of algebra. I got my velocity, which is V sun, and I got a VR sun and VT sun. And I've got the velocity of the star. I got VR star. VR is the radial velocity, is just the motion of the star, which is what I'm looking for, minus the motion of the sun. That gives us the relative motion of that star. Same thing, VT is the relative motion of the star. VT star is its motion. VT sun is our motion. Do a little bit of geometry with the angles, and you work out that VR is this little complicated formula, but what we've done is we've gotten rid of this other VL star with a little bit of geometry. And this works out to omega minus omega naught. Omega naught is our rotational velocity, and omega is that star's rotational velocity, times r naught times sine of L. So this is getting useful. And we have a similar relationship for the tangential velocity. And then you do a little bit, so this is useful, but I have too many unknowns and it doesn't actually answer what I want. What I want is d omega dr. So I'm going to rewrite this as d omega dr, because I've got omega minus omega naught. A minus b is a derivative, as long as a and b are close, and you divide by something. So you got to wave your hands a little bit. Once you've waved your hands, you're left with a formula like this. The radial velocity is this number times the distance times the sine of the angle. Now, what we do in this algebra process, it's not very hard, it's just boring. What we do is we replace all the things that are hard to measure with things that are easy to measure. Now, okay, D is hard to measure, but for the close things, we can mostly do it. So what this says is this is the radial velocity that I measure. That's the important thing, is I'm relating things that I can measure to what I want, which is the rotation curve of the galaxy. So this is the thing that I measure. This is what I want. This is the sun, so I have to get rid of it. So we do a little bit of algebra to get rid of everything else, and we're left with A, which is some constant that's true for all of the stars, times the distance to each star, times the position on the sky of each star. So think about this. Think about what you're looking at. You're looking at we've got the sun, and we've got stars that are all not everyone's going that way. They're all moving with us. So here's the galactic center down here. They're all moving on arcs. I'm going to look around. This is L. This is the galactic longitude. This is where I'm pointing my telescope. So we can make a map between the velocity and where I'm pointing my telescope that's relatively smooth. As long as everything's well behaved, we know that VR is just some number times the distance times the sine of 2L. As I turn my camera around. Now what this gets me is I can measure VR for all of these stars. I got to measure VR and D. L I don't have to measure. That's just where I'm pointing my telescope. That's a knob I have. D you got to measure. VR you got to measure. And that gives you A. A is here, is related to the slope and the value of the rotation curve. So you measure these two quantities and you get that the rotation curve at the solar circle is flat. Did I not put up? I didn't actually write down the values of these numbers. Anyway, what you get is that the value of the rotation curve is flat. So what's the purpose of the Oort constants? So the Oort constants relate the 3D velocities that the stars have to the rotation curve that I can measure. But it requires all three components of the velocity, but we can make it not quite so noisy by doing everything at once. So by fitting a whole population of things that have these properties, we can get the rotation curve pretty easily. Oh, there it is. Anyway. So this is what this measurement would look like. So if we were just in a disk that has some differential velocity, the radial velocity as I turn my telescope around, the radial velocity is when I'm looking that way, it's maximally small. When I'm looking that way, or when I'm looking this way, it's large. When I'm looking this way, everything's tangential. When I'm looking that way, everything's coming at me. So you can see we've got this circular behavior to what you perceive as the radial velocity. Measuring derivatives is very difficult. This is the upshot. What we want to measure is a derivative. Measuring distances is hard in the first place. We need to get the derivative out of it. So this relates things to the derivative. So the center of the galaxy is easier in some ways and harder in some ways. It's easier. It makes more sense. The cool thing that you can do is this is actually kind of awesome. The rotational velocity is decreasing from the center outwards. And as long as it's decreasing, then I can use this trick where if I draw a line out in this direction, so this is just, I'm pointing my telescope over there, and I measure the velocity of all of the things along the line of sight. So my measurement looks like this. So this is V relative to LSR. Remember, that's local standard rest. That's our motion in the galaxy. So V is velocity, and this is galactic longitude. And what we're seeing is a radio measurement of carbon monoxide. So you take your radio telescope, you point it over there, you measure all of the CO flux in a bunch of different velocity bands. So radio telescopes are cool because they give you a bunch of different frequencies at once. So you get a bunch of different velocity components at once. So I point my telescope out that way, and I see clouds that are close to me, and I see clouds that are further away from me. And depending on where those clouds are in the galaxy, they're moving at different speeds, and I can tell. So when I look at, say I look out here at -20, I see all kinds of stuff. I see the bulk of the stuff is here at a velocity of, let's say, what's that? So that's 200, that's 100, that's 50, that's like 25. So this is a velocity of like 25 kilometers a second. So we've got a bunch of stuff there, but we've got some things that are moving at different speeds too. So those are things that are closer or further away from us that are moving at faster or slower velocities. Now the fastest of these is at the outskirts. So I just need to measure what the fastest of these is, and I have what the furthest out object is. So so this is a nice trick. Oh, where did my... Huh. Oh, man. Past me updated the slides and took some stuff out. that I like. Let me go see. Give me 1 second. Because this makes more sense if you can see it. So. Bear with me 1 second. Oh. Pass me as a dick. Yeah, that's the one I want. 7. So what the tangent point method gets you is this. Let's go here. So as I'm looking out along this line of sight with my radio telescope, I see all of these clouds at different velocities. And this guy is going to be moving slower than this guy because v squared equals gm over r. So velocities tend to fall off with radius. Right? So this guy's moving slower in absolute than this guy, but also I'm seeing this one at a steeper angle than this one. When I look at this one here, I see all of the radial velocity because I'm looking along its velocity. So this cloud, the measurement that I measured, is in fact its velocity. For this cloud, what I measure is its velocity projected along the line of sight, which is going to be small. This one, its velocity is small and its projection is less small. This one, its velocity is big and the projection is big. That makes sense? So if I plot the intensity as a function of wavelength, I have this kind of messy blob of all of these things, but I can sort out which one is which. So this blob here is at a longer wavelength because it's moving away from me faster. So it's been Doppler shifted more. So this thing here is this guy here. Now, I know that I see all of the velocity and I have a pretty good idea of where this object is. So I know exactly where it is along line of sight. So here's my galaxy, here's the sun. I point my telescope out this way and I see this cloud. So provided I have clouds everywhere, which I do, when I make my measurement, I see my fastest moving cloud is the one that's closest in. I know, not only do I know its whole velocity, but I also know its geometry. I know where it is. I know its distance. Because I know R0 and I know the angle where I pointed the telescope. What I want is velocity as a function of position. And this gives it to me really directly. Because I make a measurement, I just look at a bunch of clouds, I pick the fastest cloud, and I know where that cloud is by the geometry. Just R is, how does this work? SOHCAHTOA. This is opposite over hypotenuse. So sine of L is R over R0. L is where I pointed my telescope, and R0 we already sorted out. So I know the distance to this guy, and I know its velocity. So this tangent point method, so for the tangent point method, what you do is you make a radio measurement. At some galactic longitude L. I know that the fastest cloud is that R equals sine L over R naught. No, R naught sine L. Do that. I know where it is, and I know its velocity. So I get V of R interior to the cloud, just using interior to the galaxy, just using radio telescope. So that's pretty cool. And the last method is just measuring it by brute force. Let's see. Here I went through that with more detail, but so the last region, so measuring stars that are interior to the sun is easy because we have this tangent point method. Measuring stars that are close to the sun is easy because we can measure all three velocity components and use statistics to beat down all of the uncertainties. When you get outside of the solar circle, when you're too far away to really use proper motions, then you have to infer what the proper motions are. So this is the rotation curve of the galaxy, and there are more modern rotation curves, but they still look like this. What do you notice about this? So you notice that it's peaked, and there's a peak in the center, and then it falls off. So that's the bulge. So we got a bunch of stuff in the center, falls off like that, and then it transitions to the disk. Things speed up a little bit once you have the whole disk interior, but then by us, this velocity really should start falling off again. And we see that it doesn't, and maybe it increases a little bit more. But the measurements are really wide. So these are the measurement errors for each one of these stars. Each one of these points is a star in the galaxy. And these ones out here, their rotational speed is a large error because we can't do the proper motion very well because they're too far away. We can do the radial motion pretty well, but the proper motion is hard to do. And you need to know exactly what that star is doing. I think that's everything that I care about for our motion in the galaxy. So, yeah, so the next... yeah, does anybody have any questions about any of those? Tangent point or constants? I'm not going to go, there's not going to be a ton of questions other than pretty superficial questions on these because they're kind of data driven and I don't have a lot of data heavy homeworks. Maybe someday I will. But, yeah, so let's move on to, I'm going to jump the gun a little bit and start talking about galaxy classifications. Oh, wrong semester. All right. Oh, huh. Sorry. For those viewing at home, that was me dragging the camera around because I forgot which window is which. Where's the thing that I want? Here's the thing that I want. Okay, so let's talk about classification of galaxies. Let's get out of our galaxy. There's basically two kinds of galaxies. There's spiral galaxies and there's elliptical galaxies. That's a total lie. There's hundreds of different kinds of galaxies. But for the most part, they're either big round honkers or big flat disky honkers or little weird guys. So I guess there's three classifications. There's big rounded things, there's medium disky things, and there's little weirdos. The spirals, let's talk about the spirals first. Well, okay, let's talk about Hubble's tuning fork, because Hubble's tuning fork collects all of these things into a morphological scheme that is completely wrong. And packed us with this terminology that I hate. There are some things about astrophysics that I will complain about. And this early, late, astronomers love to dub things early and late type when they have no idea what it is. So Hubble looked at all these galaxies and said, things get more complicated. So these round things evolve into these smooth spiral things, which evolve into these really spirally spiral things, which evolve into these little dudes, like Pokemon. Like they get bigger and more complicated. But that is in fact backwards. So early type galaxies are big honking ellipticals. Early type spirals are big spirals that aren't forming much stars. Late type spirals are actually younger objects that are forming stars aggressively. So the early late terminology, whenever you hear anything talking about age in any way in any broad strokes, take it with a huge grain of salt, because astronomers can't let go of bad terminology. So we have this fork that we use a lot. I mean, you got to organize stuff, so it's a fine way to organize things, but you can't infer any evolution history from this. So we basically, things are elliptical or spiral. Well, okay, there's lenticular galaxies. Those might be something different. Let's talk about those in a second. So let's talk about spirals, or let's talk about ellipticals real quick. Ellipticals are real easy to classify from this old school observational method. It's just, are they football or are they soccer ball? That's really it. Football or a football. Either they look like this, or they look like this. Also a football. So what's the difference? The difference is the axial ratio of the semi-major to semi-minor axis. So E is the short axis over the long axis. The label for the galaxy, -1, is 10 times E. So if the two axes are close to equal, then the eccentricity is 0. And if they're really elongated, then the eccentricity goes up to 1. So we multiply that by 10, because that number varies kind of between 0 and 1, to get the classification of the galaxy. So an E4 galaxy has an aspect ratio that's about 4 to 1. What does that work out to be? If it's 4, then this is 0.4, so that's 1.4, so the galaxy is like 50% wider than it is thick. So that's a pretty elongated object. Spiral galaxies have several different classifications that we'll talk about in a second. Let's look at some pictures. So A to B, these are axis ratios. I like these old school photographic plates. They're terrible when you scan them, but actually looking at one of these plates is really amazing, because they've got photographic resolution. So this resolution is shit compared to grains of sulfur. So an actual photographic plate like this is one of the most beautiful things, because you can really see this whole galaxy there. But anyway, so this is an E2 because somebody sat down and carefully measured these widths. This one is an E0. This one is a 5, and here's a 7. This one might not be an elliptical galaxy. That actually might be a lenticular galaxy, but it's an elongated galaxy. So they vary from 0 to 7. Within ellipticals, there's a bunch of classifications. So there's normal ellipticals, which is the kind of bulk things that we'll talk about. There are giant ellipticals, which you find in the center of galaxy clusters, and these objects are really, really large. There are dwarf ellipticals that have low surface brightnesses, but we're not going to talk too much about the weird dwarf spheroidals and dwarf elliptical galaxies. A CD galaxy, C is for large and D is for diffuse. This is from a different classification system than Hubble's. These are really large, bright galaxies that form in the center of galaxy clusters, and they are just huge monsters. And there are some little guys that are pretty faint that are important. These littler elliptical galaxies are useful for understanding where all the stuff is in the galaxy. We want to understand the statistics of galaxy distributions. Our understanding falls down with the little things. But Spiral galaxies have a much more complicated naming system because they're much more complicated objects. So, and this nomenclature is just terrible. Just awful nomenclature. But we'll talk about it anyway. So S is for spiral. And then there's an A, capital A, or me, or nothing. So A, there is not a bar there. It's a dry county like half of Kentucky. B means there's a bar, so you can go relax. And nothing means there's not a bar. Just like A. A is just being explicit about it. Then you have A, B, C, D. So this is bar. This is the openness of the arms. Or bulge to disc. So little a has a large bulge. And D does not have much of a bulge at all. So the bulge size is really the important thing, I think, to look at. That's how they really classify things programmatically when they're like actually doing measurements and assigning numbers. And there are splits, so there's A, there's AB, there's B, there's BC, C, CD, blah, 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 blah. And this opening angle varies from a few to 16 degrees. And I'm only going to have you classify things kind of loosely. So this, about the big A, that's Hubble's classification system. There's a big A, this is the Vacalura's classification system, which also adds on ring or arms. Not. So if there's a ring, then it can sometimes have an R. So let's see, I have a whole page of these right now, right? Uh-oh. Was that? Yeah. I'll pull up a second. I'll pull up a couple in a second, but I gotta make sure I don't die. In my last 4 minutes of class. That tells me I can almost make it through the whole class. Let's see. Let's see. Here's the Vacalures. Here's some with rings. So here are some with rings. So not all the rings are quite as pronounced as Sombrero. Sombrero has a ring that's like most of the galaxy, whereas a lot of these things have rings that are kind of little, and it's just kind of near the bar. So these rings are small. Yeah. As far as the classification happens, yeah. So most of the rings in the spiral arms are processes that are happening in the gas in the galaxy. And the gas in elliptical galaxies is all really hot, so it doesn't do very much, and there's not very much gas in the first place. So elliptical galaxies don't have quite as many interesting features because they're really hot. Okay, the Morgan classification system. So we talked about Hubble, which doesn't have this, doesn't have this. The Vacalures, which has an A when there's not a bar and classifies things as an R and an S. This actually gets used kind of interchangeably with Hubble. And then the Morgan classification system, the only reason I bring it up is because it's why we call things CD galaxies. There's a whole host of ways to talk about what's in a galaxy. Here is a really cool thing. I gotta put this poster up. So this poster is a really cool, and I've got a hard copy of it somewhere. I should probably hang it on a wall. It's a really cool graphic that shows what all the galaxies, different kinds of galaxies look like. So here is an SBC, so it's got a medium-sized bulge. It's got a really pronounced bar. This one has a ring. In these classifications, they don't note the ring, but this one's got a ring. And maybe there's a bar, but probably not. And this one is an SB. This is an SBAB. So the big B here is for it has a bar, and the AB is for its bulge to disk ratio. So those are barred galaxies, and then unbarred galaxies are up here. I'm going to put the very large PDF of this whole poster on the notes in the files because it's very cool. I'll tell you about it at some point. Oh yeah, I'm gonna zoom way the hell out. That's fine. One of the things that, and I'll talk about this. No, go away. There you go. Come back. One of the things that we're going to talk about a lot, and this is a graph that I would like everybody to get comfortable with, is I talk about one of the things that led Hubble to come up with this backwards naming scheme is he didn't have masses for these galaxies. Measuring masses to galaxies is difficult, and Hubble couldn't do it. Hubble was just looking at pictures. They didn't have a lot of the techniques that we've got now. Now that we have masses, we can understand things. So this is a plot that I'm going to show you now, and then I'll stop talking. But we're going to see this again. So this is a distribution in 2 dimensions of color versus magnitude. So it's another color magnitude diagram, just like we saw for HR diagrams with stars. But for reasons that I don't really understand, it's transposed. The magnitude is on the bottom, and the color is on the side, but that's fine. So here we have rest frame U minus R. Okay, U minus R is a color. It's the U band over the R band. Rest frame U minus R, what does that mean? What does rest frame mean? What does rest mean? Still. So rest frame color, so the rest frame U minus R is the color in the rest frame of the galaxy. What happens to most galaxies in the universe? They're all redshifted, so they all look redder than they should. We got to take that out. So this rest frame U minus R means it's the U minus R, we just took out the redshift. And then down here on the magnitude, so this is color. Magnitude is MR minus 5 log H70. What's MR? That's an absolute brightness in the red band. Does that make sense? And this 5 log H is annoying as hell. This is because all of our units, when we have extragalactic measurements, all of our measurements are in H inverse megaparsecs. Because the H inverse packs away our ignorance about how the universe is actually expanding. So this H inverse says, well, okay, if we learn cosmology better later, we can fix it. So what's in it? So we've got the brightness. So, okay, which direction is brighter on this scale? Are brighter things over here, or are brighter things over here? Everybody together? Left. So brighter is going that way. You can tell because the number is going down. Because that makes sense. So these guys here, so you can see these curves, and within the curve is how much stuff is in that region of space. So we have 2 big peaks. We have a big peak here. This is dim and blue. This is bright and red. So we have a dim blue streak and a bright red streak. This is bimodal color distribution is how we see galaxies distributed. So elliptical galaxies are on this big red line, and spiral galaxies are on this small blue line, and they travel from one side to the other. I'll bring this plot up again in the future. But that's all I gotta say for today. Any other questions on anything? Good.